Welcome to the online video lecture series of the course Computer Organization and Architecture. So, in this unit we have talked about memory hierarchy, and we have discussed various types of memory, and we have also talked about how cache memory is mapped with the main memory and various mapping schemes. So, in this particular lecture we will talk about virtual memory and its implementation. So, what is virtual memory? It allows users to construct a large size programs. So, whenever the size of program is greater than the area available in main memory, so this concept can be used. Or we can also store various types of programs or different programs or multi programs in a single memory space. So, that concept will help to store, and we can also distinguish all the programs and corresponding data or logically related data to that program through this particular concept. It allows efficient and safe sharing of memory among multiple programs. So, if it also supports multi-programming architecture, or you can say dynamic programming can also be possible through this particular system or this particular concept, and the data can also be safe or protected through this particular system or this particular architecture. So, virtual memory is the concept through which the big size program or multi programs can be stored in a system. So, let us talk about basic concepts which are used or terminology which is used in this particular concept. So, first, virtual memory translates the program's address space to physical address, enforcing protection of a program's address space from other programs. So, what is address space? Where the programs are stored. Address space is nothing but an address used by programmer is called virtual address, because programs where the programs are used, or you can say the auxiliary memory which is used to store big programs or multi programs. So, that particular area can be called as virtual address space or address space. It is abbreviated as VA. And the memory space, which is nothing but a main memory area where the programs are stored which are currently needed by the processor, or actually the program which are directly fetched from where by the processor, or processor directly fetch the data or instruction from main memory. So, that particular area will be called as memory space or M. It is denoted by M. So, memory space is the main memory area, and the addresses called as physical addresses. Here the addresses, whatever addresses we use, are called as physical address or denoted by PA. Obviously, in this particular concept we can understand the virtual address space or address space will be greater or equal to the memory space. So, a virtual memory block is called a page. So, whatever data we have stored in our program we have stored in virtual memory or in address space, they are in terms of, they are stored in terms of pages. So, page will have some number of words or number of lines, and virtual memory miss is called page fault. Whenever page is referenced by the processor which is not available in main memory, so we can call as this particular reference as page fault, or the page which is not available in main memory and it is referenced by the processor, then we say this phenomena as page fault. So, virtual memory produces a virtual address translated by software and hardware combination to a physical address. So, we have to understand in this particular lecture how address space or virtual address are converted or mapped with the physical address, because virtual address is the address used in case of address space, and physical address are the addresses used in memory space or main memory. So, let us take one simple example, the main memory capacity is 32K words. That means 32K words can be stored in main memory. So, obviously, this will come as 2 to the power 15. So, 15-bit address are needed to specify physical address. So, physical address will be having 15 bits, and auxiliary memory, or you can say virtual memory or address space, can store 1024K words. So, obviously, it will take 20 bits, because this will come as 2 to the power 20. So, here the virtual address or address space is 1024K and virtual address will be of 20 bits. So, we have to map we have to understand the mapping between these 20 bits to 15, virtual address to physical address. So, this way we can write the memory space and address space. So, M will be 32K and N will be 1024K. Obviously, the mapping, if virtual address is given to us and we have to map, or we have to calculate the physical address corresponding to that virtual address. So, mapping table is required in that case. So, we have to understand this mapping table. So, let us talk about the same example. For example, virtual address is having 20-bit address and physical address is having 15-bit address. So, memory space is given in terms of 32K and address space is given in terms of 1024K capacity. So, 20-bit address is used here and 15-bit address used here. So, we have to map this virtual address to physical address. Here the various programs and corresponding to those programs, the data are stored in physical address or auxiliary memory. And here only those programs or data are stored which are currently needed by the processor. So, we have to use the mapping table to map from virtual address to physical address. So, this is a mapping table used to map. So, this 20-bit address is given to this particular table. This table will provide 15-bit physical address. So, 20-bit address is given as input to this particular table, and corresponding to that 20-bit address, the data or the value or the mapping value which is produced by this mapping table will be a physical address of 15 bits. So, here mapping table simply map the 20-bit virtual address to 15-bit physical address. So, we provide the input to this table and this table will provide or will give a physical address corresponding to that entry. This table will give a physical address, and this physical address which is related to main memory, some area of some block of main memory. So, in this particular concept of virtual memory, the auxiliary area or auxiliary memory area or virtual memory area will be given as in terms of pages, or you can say there are various pages which are stored in virtual address. So, virtual address or virtual memory will store number of pages. However, main memory will be divided into number of blocks, and different blocks will be loaded with different pages. So, at a time few pages are loaded into a particular block of main memory. So, let us talk about one example. There are two examples shown to understand this particular concept, how pages are mapped with the block of main memory, pages of virtual memory and block of main memory. So, one example, block size of 1K word given and page size is 1K word. Obviously, we have to transfer the page of virtual address or auxiliary memory to particular block of main memory. So, obviously, the size of block will be equal to the size of page, or you can say page size and block size must be equal, because whenever the page is referenced by the processor, that page must be available in main memory, and if the size are differed, so that page cannot be stored in a specified area or block of main memory. So, in that case that number of pages or page replacement is not possible or will be very difficult in that case. So, page size and block size will be same to understand this concept. And here main memory capacity is given as 32K words or you can say 32 blocks, because 1K word is the size of one block. So, there will be 32 blocks. And auxiliary memory capacity is given as 1024K, which is the same example as we have discussed. So, obviously there will be 1024 pages. So, let us take one simple example or small example where block size is 1K and page size is 1K. Both the size of block and page is same. And the address space is given as 8K words and memory space is given as 4K words, or main memory capacity is 4K words. How many number of pages and how many number of blocks? So, let us calculate. So, here address space, pages are stored in auxiliary memory area or in address space, or address space is divided into equal size pages. So, obviously, so 8K divided by 1K, because one page size is 1K. So, there will be 8 pages in address space. And how many number of blocks? In same way we can calculate. 4K is the size of main memory as given here, and 1K is the block size. So, it will come as 4. So, you can understand this way there are 8 pages given in the address space or in auxiliary memory area, or 4 blocks are available with main memory or memory space. So, we have to map these 8 pages with 4 blocks. So, mapping between 8 page to 4 block is required. Now, in this case address space is 8K. So, 13-bit address is used for virtual address and memory space is 4K, that is 12-bit is used for physical address. So, mapping between 13-bit to 12-bit, this is virtual address and this is physical address, because virtual address is given in 13 bits and physical address which is used here is 12 bits. So, mapping between 13 bits to 12 bits is required. So, again we will use this memory page table. Now, one example is given 101 0101010011. This is the virtual address of 13-bit given in this particular case, and we know 8 pages resides in auxiliary memory area or in address space. So, 13-bit address or the virtual address will be of 13 bits, and at a time only 4 pages can transferred or reside in the memory block area, because there are 4 blocks in main memory. So, at a time we can transfer only 4 pages here. So, how this mapping can be done using virtual memory concept. So, here memory page table or this mapping table is used for this particular case. So, we know 13-bit address will be mapped with 12-bit address, which is given here. 13-bit virtual address will be mapped with 12-bit physical address or physical or memory address. Now, first we have to calculate which page number will be available with which particular block. So, how this can be done? So, first this virtual address is divided into 2 parts. First part is page number, which will be of 3 bits. Why? Because there are 8 bits, there are 8 pages. So, 8 pages means 2 to the power 3. 3 bits are required to map or to address these pages, 8 pages. So, 3 bits are used for page number, and one page will be having 1K words. So, which is nothing but 2 to the power 10. So, that is why 10 bits are given for line number or word, particular word. So, this way we can use this concept of mapping. Here 3 bits are given for page number, and there are 4 blocks, as we have said there are 4 blocks, only 2 bits are required to map these blocks. So 3 bits of page number will be given to this page table, and we can see corresponding the entry of particular page, the block number will be issued. For example, 101 page number is given. So 101 is given here, and corresponding to this page number, block number 01 will be issued by this page table. So 01 will be issued or provided. So 01 number of block will be appended or concatenated with the line number which is coming from this location. So this is virtual address divided in 2 parts, page number and line number. So line number will be copied as it is and concatenated with the output of this particular page table to get the actual physical address. As you can see, there are 4 pages available in different block location. Page number 1 is available with block number 3, page 2 is available with block number 0, 5 is available with block number 1, page number 6 is available with block number 2. And corresponding to these blocks which are available in corresponding to these pages which are available in different blocks, the bit, or you can say the presence bit, is enabled. It is given as 1 if the page is available in main memory. So as this table shows, page number 1 is available with block number 3. So corresponding to this entry, the presence bit is 1, and if it is not available, for example this page number 011 which is not given in this or available in this main memory area, so corresponding this entry is 0. So this way we can understand the concept of memory page table. So presence bit 1 if the page is available in particular block, presence bit 0 if the page is not available, or if this page is a reference which is not available in the main memory, the phenomena is called as page fault, or you can say operating system will declare it as a page fault. So there are a few drawbacks in this particular case. That was the simple example or a smaller memory capacity example. If we are taking big example as shown in this particular case, here the address space capacity is 1024 pages, and the main memory capacity is 32K words. So there are 32 blocks and 1024 pages. So you can understand we have to map these 1024 pages to 32 blocks. At a time only 32 pages can reside in main memory, and corresponding to these pages which are available in main memory, the presence bit is 1. So only 32 entries are present, remaining 992 entries are empty, or corresponding to these 992 entries are 0, or page presence bit corresponding to these entries 992 entries will be 0. So these are empty spaces. So if the auxiliary size or virtual memory address space is having large space or big capacity, and your main memory size is very little or small in comparison to auxiliary space, so in that case there is a chance of more number of empty entries in the page table. So we have to avoid this using auxiliary memory concept, associative memory page table. So this concept is used to use the efficient mapping scheme, or this particular concept is used to utilize fully the memory space, or efficiently we can utilize the memory space in the page table. So here the page number and corresponding block number entry is given in the page table. What we can do in this case, number of words equal to the number of blocks in main memory. In this particular case, we have to enter only those number of words or entries which are available in main memory. So this table will be maintained in such a way so that only those entries will be there which are available, or page those pages are available which are available in main memory or which are present in main memory. Those entries corresponding block numbers, entry of a pair of page number and block number will be stored in this page table. The memory is reduced and each location is fully utilized. In this particular case, there is augment register. So, if any page is referenced by the processor, so that particular page number will be matched with all the entries of the associative memory page table. And if match occurs, this page number of given address, if it is matched with the one out of these 4 entries, then corresponding block number is transferred to the main memory. So, this way we can design, we can reduce the empty spaces, as we have seen in previous case. So, more number of empty spaces can be reduced in this associative memory page table, or using this concept we can reduce the empty spaces. So, here whenever processor requests for particular page, so that page number will try to match all the entries with all the entries of the associative memory table. And here you can see the pair of page number and block number is stored only. There is no requirement of presence bit. So, 101, we can see 101 is matched with this particular entry. It will start matching from first to last, and here the 101 page number is available, and corresponding to block this page, the block number 01 will be transferred, or you can say this block number will be concatenated here to get the actual address of particular page or word line. And if match does not occur, the address provided by the processor, the virtual address is issued by the processor, and that page number is not available in the table. What will happen? Obviously, the page fault will occur, or in that case what will happen? We have to replace the page, because that page is not available in main memory. So, operating system, there is a call to operating system, and operating system will manage particular page which is required or referenced by the processor. So, if the page is available or match occurs, then this phenomenon is called as hit, or that page is transferred to the processor from the main memory. And in a associative mapping or in a memory page table, if page does not match, or the entry corresponding to particular reference page is not available, or presence bit is 0 corresponding to that page, what will happen? Then there is a page fault. And in case of page fault, there is a call, or operating system will manage the page replacement, means that page will be replaced with some available page. Here it is shown. For example, the page py is requested by the processor, and this page is not available in the main memory. So, this page will be replaced with some page px, which is available in main memory. So, how this page replacement algorithm will replace the particular page of which page of the main memory? So, we have to understand this page replacement will be based on these 3 questions. So, which page has to be replaced, and when this page has to be replaced, and where this has to be replaced. So, whenever page fault occur, the operating system is called, and the operating system will manage this page. So, algorithm of page replacement will run in background, and particular page will be replaced with some page of the main memory. So, page replacement algorithm will run in the background on the basis of these 3 concepts: which page has to be replaced, and this when this page has to be replaced and where this page has to be replaced if the page fault occurs. So, this way we can understand. So, in next lecture we will talk about various page replacement algorithms if page fault occurs. Thank you.